Okay, so let's talk about the particle on a ring. This is another simple system, and the problem looks like this. First of all, let's talk about the classical description, okay, about this particular system we're looking at. We're going to consider a particle that's confined to move on a ring of radius r. So imagine you have a circle with radius r centered on the origin. Okay, so this is your x-axis, this is your y-axis, and your particle, we're going to confine that to just move on the ring itself. So it can't be outside the ring or inside the ring, it just has to be on the ring. So we're going to define the potential energy to be 0 on the ring and infinite elsewhere. Okay, so if the particle has a well-defined energy, then that means it must be moving at constant speed. So your speed is constant, and so what's the kinetic and total energy is going to be kinetic energy, which is 1/2 mv squared, right? And the potential energy is 0. So it has a constant energy. It's moving at constant speed, going around in circles. Okay. Now, since your particle is moving on a ring, going in a circular type of motion, it's not going to have a constant velocity. It has a constant speed, but its direction is always changing. So when the particle's over here, its velocity would be pointing this way. If it's over here, its velocity would be pointing that way. So the momentum, we say, and the velocity are not constant. It's changing because it's constantly changing direction. The magnitude of the momentum, the magnitude of the velocity, the speed is constant. All right. Now, whenever you're dealing with this type of systems where you have some kind of circular motion, it's oftentimes more convenient to describe it in terms of what's called the angular momentum instead of the linear momentum. Okay, so the angular momentum is defined as, let me redraw this. Angular momentum L is defined as the cross product of the radius vector and the momentum vector. What's the radius vector or the displacement vector? That's just the vector that locates the particle right there. So that's vector r. Okay, so we put an arrow above the r. And what's our momentum vector? If my particle is over here, where is it moving? What's the direction of the momentum vector? Let's just say it's moving counterclockwise. Then our momentum vector is going to be pointing that way. Okay? So, angular momentum is the cross product of the radius vector and the linear momentum vector. And the cross product of two vectors is just, the magnitude will just be equal to the product of the magnitudes of the two vectors times the sine of the angle between them. What's the angle between the r vector here and the p vector? Here's your r, okay, and here's your p vector. In this particular case, if your particle is moving on a circle, then that angle is 90 degrees. Okay, so the angular momentum vector is a vector whose magnitude is equal to, okay, the magnitude of the r vector times the magnitude of the p vector times the sine of the angle between the two vectors. So how do you measure that angle? Imagine, okay, start with the first vector. Imagine lining up your fingers with the first vector, direction of the first vector, okay, and then curl your fingers of your right hand, and then curl them towards the direction of the other vector. Okay, so to measure the angle between them. So from R, I'm going to measure the angle from R to P. Okay, so if I want R cross P, the angle theta I want is the angle that I have to measure going from the direction of R towards the direction of P. Okay, so momentum, linear momentum is just mass times speed, right? So the angular momentum then is just equal to r times p, or r times mv. So this is L is just going to be equal to mr times m times v. Okay, so that's the magnitude of your angular momentum vector. Now, angular momentum is a vector. Okay, so where is it pointing? Whenever you take the cross product of two vectors, okay, the cross product will be pointing in a direction that is perpendicular to the plane of the two vectors. Okay, so by convention, so if in this particular case, if you have a particle that's moving in a counterclockwise direction here, okay, so your particle is moving in counterclockwise direction. So r cross p, this is your theta. Where is this angular momentum vector of this particle pointing? Perpendicular to the plane of this slide, of this screen. Pointing towards you or away from you? Okay. Use your right hand, use the right hand rule. Imagine your fingers, your 4 fingers besides the thumb, okay? Stretch out your hand into an L shape, okay? Now aim, align the 4 fingers, okay, your pinky, your ring finger, your middle finger, and your index finger. Point that in the direction of the first vector. That's R, okay, in this case. All right, now curl those fingers towards the direction of the P vector. So curl them inwards to get to the P vector. Your thumb is pointing in the direction of the cross product. Okay, so the cross product of R and P, R cross P, will give you a vector that's pointing where your thumb is pointing. Okay, so if you curl your right hand fingers from the R vector to the P vector, the direction of the angular momentum vector is perpendicular to that. That's where the thumb is pointing. Okay. So if my R was like this, okay, and my P was like this, what's my R cross P in this case? Is it pointing into the slide, into the screen, or up from the screen, outward from the screen? So line up your 4 fingers of your right hand with the vector R, and then curl it towards vector P. And where's your L vector pointing? It's pointing inwards, right? Into the screen. All right. So that's angular momentum. Now, whenever you have a particle that's moving around in a circle at constant speed, you can see that it's going to have an angular momentum equal to m times v times r, right? So your angular momentum is mv times r. R is the radius of the circle of motion. And the direction is going to be either away, it's perpendicular, either pointing away from the plane or away from you or towards you, if the plane is parallel to you, okay? So that's angular momentum. Now, so if the angular momentum is equal to R times P, okay? Then the energy, the kinetic energy is 1/2 mv squared, right? And we said before that we can always write this in terms of momentum, and the way you can imagine deriving that is multiply this by m over m. That gives you 1/2 mv squared over m. So that's p squared over 2m. So that's another formula for kinetic energy. It's p squared over 2m. And that's going to be our total energy here because we have a zero potential energy. So the energy is p squared over 2m. Well, what is p in terms of L? It's L over R. So that's going to be L over R squared over 2m. So that's going to be equal to L squared over 2mr squared. Okay? So what do we notice here? Your speed is constant, right? Mass is constant. Your mass is constant, your speed is constant, so your total energy is constant. So as long as your particle is moving at constant speed in that circle, it's going to have a constant total energy. So since mass is constant, the radius of the circle is constant, then your angular momentum is also constant. Okay, so that's the nice thing about that, is the angular momentum is constant. Unlike the momentum, the linear momentum, which is not constant. The linear momentum, it has a fixed magnitude, it's a constant magnitude, but its direction is always changing. But as long as your particle is moving in this circle at constant speed in the same direction, in the same clockwise or counterclockwise motion, then the angular momentum vector is constant. Okay? So what could make your angular momentum larger or smaller? What's the formula for angular momentum? It's mvr, right? It's linear momentum times r. Yeah. So if it's moving, even if it's moving at the same speed, right? If it's moving in a bigger circle, then that means it has a higher angular momentum. Okay. Or if it's moving in the same circle, it can move faster on the same circle, then the angular momentum would be higher. Okay, so those are the two things that could affect the value of the angular momentum.